We are now at the most advanced frontier of BESS systems operation engineering, the integration of artificial intelligence and digital twins to maximize availability, efficiency, and service life while minimizing failures and OPEX. A digital twin is a dynamic virtual representation of the physical system, powered by real-time data and predictive models. The features of the digital twin shown are hybrid physical plus machine learning modeling continuous update between 1 and 1.5 minutes. Operating accuracy of plus or minus 1.5% for state of charge, SOH, and plus or minus 2.3% for future capacity. It allows for anticipating degradation, simulating thermal responses, and automatically adjusting set points before failure occurs. We can see a clear comparison between the traditional approach and the AI-based approach. The traditional methodology is based on fixed intervals. Based on time or number of cycles. Reaction to a failure that has already occurred. And AI prediction is early detection of hidden patterns. Real-time analysis of system status. Optimization of intervention before failure. The models commonly used are LSTM, long short-term memory, random forest. Autoencoders. This translates into quantifiable benefits of less than 42% reduction in maintenance tasks and more than 95% accuracy in early detection. This reduces downtime, prevents diagnostic errors, and improves overall efficiency. AI is also used to manage differential aging between modules through adaptive balancing at the module level, optimizing SOC/SOH. Multi-objective decision making, prioritizes LCOE versus useful life versus available capacity. Reinforcement. Learning. The system learns to improve its charging-discharging strategy based on historical performance. Therefore, results can be obtained such as more than 15% improved lifespan. Less than 22% degradation. More than 8% improved system availability. We also see the direct application of AI in predictive thermal management, such as thermal control curves comparing conventional control, predictive AI control, and the recommended thermal limit, approximately 40 degrees. Some features include local analysis with latency less than 10 milliseconds, edge computing, dynamic load distribution. Anticipatory cooling by predicting thermal peaks. Detection of thermal clusters or hotspots. Some results can include a reduced temperature increase of between 0.3 and 0.5 degrees compared to conventional systems. This helps prevent thermal runaway, improve HVAC efficiency, and increase thermal safety without oversizing systems. With the application of AI and digital twins, we are moving from preventive maintenance to adaptive maintenance, and from reactive control to intelligent and autonomous control. So far, we have seen how to control, protect, and extend the lifespan of the BESS system. But the true value is maximized when the system operates strategically based on market, weather, and technical conditions. This block addresses the optimization of energy dispatch using advanced algorithms such as multi-objective optimization algorithms. The graph shows the optimal solutions that balance battery lifespan and LCOE. With this, we achieve the objectives of minimizing LCOE. Maximizing lifespan. Maximizing arbitrage revenue. Achieving results of between 12 and 18% in LCOE compared to conventional strategies. These algorithms dynamically choose the optimal time, duration, and intensity to charge and discharge the system. Mathematical modeling of dynamic arbitrage. The graph on the right represents a daily energy arbitrage strategy, where the red curve is the hourly electricity market price, and the blue curve is the state of charge, SOC, of the BESS system. Some of the features include the stochastic model, integrates uncertainty and price volatility. Optimization, can participate in multiple services simultaneously, frequency, arbitrage, firm capacity, etc. Improved ROI, between 28 and 35% compared to simple off-peak PVP arbitrage. This makes the BESS a financial asset managed in real time, not just an energy asset. The system must comply with internal and regulatory limitations, minimum SOC, between 15 and 20% maximum SOC, between 90 and 95% loading/unloading ramps, between 0 degrees Celsius and 1 degree Celsius per minute thermal limits, less than 40 degrees Celsius at critical nodes. Other important restrictions include EESO regulations, TSO guidelines, and the useful life and degradation models integrated into the algorithm. Therefore, comma optimization cannot be achieved without taking these physical and regulatory constraints into account. For example, in a practical case, a 100 MW hybrid PV plus BESS plant achieved results of less than 24% LCOE, an 18% increase in net revenue, a 3.2-year ROI, and a system availability of over 95%. The keys to success were multiple scenarios, spot market, PPA, capacity services, adaptive strategy, adjustment every 15 and 60 minutes, seasonality and meteorology, integration of climate models and historical demand. This adaptive dispatch strategy with AI and a digital twin is the best way to extract value from the BESS without sacrificing useful life. With these optimization techniques, the BESS becomes an operational, technical, and financial profit center. After analyzing design, operation, control, and optimization, we come to the key point: how to make sound technical decisions when designing a BESS system. This slide summarizes the essential criteria to consider based on the climate, chemistry, system objectives, and project constraints. The climatic environment directly influences the type of battery, the cooling system, and the physical structure of the BESS. For a warm climate, greater than 35 degrees, use liquid cooling with redundant heat. Exchangers. LFP chemistry is preferable, better thermal performance. Oversize the HVAC by plus 15-20% for a cold climate, below 0 degrees. An active preheating system is required. Thermal insulation of ducts, cables, and cells. NMC is not recommended. High capacity loss at low temperatures. For high humidity, greater than 80%. IP65 protection. Anti-corrosion coatings. Active and passive drainage. For seismic zones, reinforced anchoring. Seismic dampers. Containers with structural separation and firewalls. These recommendations are not optional. They are design requirements if the desired lifespan and availability are to be met. The table compares the three battery technologies, LFP, NMC, and flow, according to 5 weighted technical criteria: energy density, lifespan, cycles, thermal safety, CAPEX, and PV compatibility. LFP technology is generally the most robust option for hot climates, high security projects, and integrated PV plants. Every BESS project must pass this checklist before entering the engineering phase to verify the grid connection and capacity study, the analysis of power flows and constraints, the climate and environmental assessment, battery degradation modeling, regulatory compliance, UL 9540A, IEC 62933, NFPA 855. This initial assessment avoids costly redesigns in later phases of the project. Some final engineering recommendations include optimal hybridization, BESS PV ratio between 0.5 and 0.7 for firm capacity, and 0.2 to 0.3 for energy arbitrage. Modularity. It is preferable to scale in blocks of 1 to 5 megawatt-hours to facilitate maintenance and availability. Advanced thermal control. Improve service life by more than 15% and less than 20%. FAT/SAT testing. Mandatory with objective metrics. ML prediction. Integrate AI models from the design phase to adjust aging and dynamic behavior. These recommendations are the result of integrating operations, regulations, profitability, and safety into a single technical vision. To conclude this video, let's summarize the 6 technical pillars we've developed throughout this video. Each of them is essential to ensuring that a hybrid PV plus BESS plant is efficient, safe, profitable, and scalable. Integrated electrical design. selection of optimal AC-DC topologies according to the use case. Bidirectional inverters with fast ramps and grid-forming capabilities. Advanced synchronization with IEC 61850 and OPC UA protocols. A good electrical architecture reduces losses and improves dynamic plant control. Modular architecture. Scalability based on racks, containers, and blocks from 1 to 100 megawatt hours. N+1 redundancy and selective maintenance. BESS. PV ratios tailored by application. Shifting, firm capacity, arbitration, etc. Modularity equals operational flexibility plus reduced mean time to repair, MTTR. Thermomechanical engineering use of CFD and liquid cooling for extreme climates. Structural analysis for seismic and humid environments. Multi-level predictive thermal control, cell, module, system. Extending lifespan by more than 20% starts with thermal design. Lifecycle management. Predictive electrochemical models, SEI, microfractures, impedance. Charging strategies that optimize LCOE, limited DOD, multistage, extended CV. Thermal control and aging with AI and digital twin. The battery is a living asset that requires adaptive monitoring and intelligent maintenance. Safety protocols. Detection, alarm, suppression, and isolation systems for thermal and electrical faults. Full fat SAT test validations with regulatory criteria and network testing. LVRT, black start, ride through. Post-mortem diagnostics with CT, chromatography, and BMS log analysis. Safety is not reactive. It must be designed, tested, and audited from the engineering phase. Control integration, EMS, PPC, BMS, SCADA communication with open protocols.
Jerarquía de control multinivel. Planta, inversor, módulo, sincronización con latencias menores de 100 milisegundos para regulaciones primarias. La planta BESS no debe seguir órdenes. Debe pensar y anticiparse con algoritmos IA integrados al despacho. En resumen, un sistema BESS Utility Scale bien diseñado no es un simple almacén de energía. Es un sistema de ingeniería compleja, con lógica autónoma, modularidad inteligente y funciones estratégicas para el mix energético moderno. Espero que te hayan gustado esta serie de videos y que te sirvan para tu día a día los comentarios reflejados en estos videos. Mándame un mensaje privado por LinkedIn y estaré encantado de recibir tus comentarios de forma constructiva para futuros videos. Muchas gracias y saludos con muchas baterías.